All right. So I wanted to go over the answers to that questions 1 through 4 from the packet. So here goes. All right. So question 1, an experiment was carried out in order to investigate the relationship between magnesium and dilute nitric acid. We put in 0.07 grams of magnesium ribbon. That just means it's literally like a ribbon you would tie. It's a thin piece of aluminum. And you reacted with a dilute excess acid, so excess acid. So they definitely, when the reaction is going to stop when all the magnesium is used up. The volume of the gas produced every 5 seconds is recorded. All right, so now here's the data. So all I did was take that data, I put it in Excel. So I did 2 columns, and then I did a graph. You could see of milliliters of gas versus time in seconds. And we get our graph. Now we're looking here at how much hydrogen is produced, not how much magnesium is used up. And this would be a common method for this because we could measure the volume of gas over time as it's produced. Read the volume after 5 seconds, read it after 10 seconds, read it after 20 seconds. So this is the graph we get. All right, so when is the reaction the fastest? Well, and then how can you tell? Well, the reaction would be fastest initially. So in the very beginning, you have the most reactant. As soon as you use up some reactant, now you don't have the most, and so the reaction automatically slows down. So if we were to graph, what that would look like, it's going to look like, so it's going to, look like this. So this graph is exactly the opposite because we're reading how much is produced, not used up. So how do you tell where the fastest would be? Well, that comes down to that, tangent, the slope of the tangent line of the graph, or the derivative if you know calculus, but we don't know the equation of the line, so you can't do the derivative, so that's why we call it the slope of the tangent line, but it's essentially the same thing. How long does it take for the 0.0 grams of magnesium to completely react? Well, it's right there, or it is, right there where the volume stops changing. How are you going to tell in the graph? You can tell in the graph because it's flat from there, so there's no change. Sketch a curve on your graph that might be obtained if you used powder. All right, so what's going to be the difference between using the ribbon and the powder is surface area. The powder is going to react initially faster, so it's going to be gone sooner, and then it will level off sooner. So it's going to reach completion sooner as well. So the faster reaction leads to a faster 70 milliliters. But they're using the same number of grams, though. So suggest 2 other factors that would alter the rate, so make it go faster or slower, I guess. Well, temperature would affect it, so we could increase the temperature. Remember how you can get a date from the prom. You got to hit them with enough energy to knock the books out of their hands. So it's all of that. Surface area. You could add a catalyst if you knew one, or you could figure one out. You could increase the concentration. So remember, add more students. Temperature was make them go faster to class. Concentration was add more students. If you're looking for a gas like this one, we could reduce the volume of the reaction vessel, because that will reduce or increase the concentration of any gas. Remember, this one only affects gases. So there's a bunch of reasons. All right, second question. So now we're collecting a gas again, but this time we used chips and we used small and large. So small chips are going to have a greater surface area. The larger chips are going to have a smaller surface area. Larger surface area, meaning there's more places for it to react, the smaller the chips you use. Because remember, it's the outside atoms that get to work. The ones on the inside are not available for reaction. They showed the students moving in packs, if you remember. What do you deduce? Can you deduce about the total mass of the chips relative to one another? The answer is they're equal. And how do we know? Well, because they both produced the same maximum milliliters of carbon dioxide. So if you use the same mass, you're going to get the same eventual mass of the product. It just won't happen at the same rate, depending on the surface area. How long did each experiment take? So you can see that one took 135, that one took 165 seconds. And how can you tell from the graph? Well, it's, again, that flat, there's where it flattens out there, there's where it flattens out there. So one's at 165, and the other one's at 135. The units, we're measuring milliliters per second, milliliters of carbon dioxide per second to be more specific. And we're adding calcium carbonate chips to hydrochloric acid. So we get calcium chloride and we get H2CO3, which is H2O and CO2, remember, H2CO3. I'm not balancing it. Actually, two that balanced it. Why is the gas produced at different rates in the two different experiments? Once again, it is an understanding of the surface area. So the larger chips versus the smaller chips. Third question. All right, so once again, we're given concentration versus time. This time it's in minutes, data. I took that data and I did the first part of the question for you, and as I plugged it in Excel, and here is the graph that we get. So we get this, curve. What is the order of the reaction with respect to A? So the only thing we're given here is either the graph or the data. And if you look at the graph, so we're starting at 1 molar. So 1 molar. So at 0.5, you could see there's 0.6, 0.8. So here's 0.5. We're right around 7 minutes. Half of 0.5 is 0.25, which is at 14 minutes. And then 0.125 is at 21 minutes, which means this thing has a consistent half-life of 7 minutes. If you look at the data, it's 1 milliliter or 1 molar, it's 0.49 or essentially 0.5 at 7 minutes. And then it's 0.25 at 14 minutes. So you can see they tried to throw you off a little bit by not making the data perfect. It is an experiment. What is the order of the reaction then? So it's first order. How do I know? Half-life, which is 7 minutes. Now, there is an equation given on your equation sheet for half-life. This only applies to first order, and it's the only half-life calculation you will have to do on the AP exam. There's a way to derive this equation. I mean, I can show you if you want me to, but it has to do with, the half of the initial concentration, rearrange it. That right there is the natural log of 2. Given that the reaction A reacts with G, what is the order? And the G is second. So A we figured out is first, and G is second. Now I should have asked for the units of K, because I think that's the most confusing part of this for most students. Notice this one's not per second, but per minute. This is molarity to the first, molarity to the third. So our second gives us molarity to the third, equals molarity over minutes. Divide both sides. So now the quick way to learn how to do this is you're always going to have a molarity on the bottom that's going to cancel with the top one, and then you might have some left over. It's always going to be one less than the sum total of the orders. So this is a third order reaction overall, 1 plus 2, which means our units for K is going to be 1 over molarity second minutes, because again, third becomes second because there's a molarity on the top, always for the rate that cancels. Last one. Actually, it ended up last 2. All right, so looking at it right away, I mean, I'm kind of seeing that it's not going to be half-life this time. But if we graph, so once again, we're plotting concentration versus time this time. And notice what happens. It's a straight line. Concentration versus time being a straight line means this is a zero order reaction. In other words, the change in concentration does not affect the rate. Rate equals K times B to the 0 power, which means rate equals K. In other words, the rate is equal to a constant. It's going to leave at a constant rate. And if actually one of the ways you can do this, because they sometimes put this in multiple choice questions, and what they will show you is that the slope is constant somehow, if you can figure that out. This particular question, they didn't do that, but you'll see, we're going to do a few multiple choice coming up where it's a little more obvious. All right, so what is the order with respect to it? It's 0. What can be said about the rate of consumption of B? It has no effect on the rate. No effect on the rate. And then the last one, question 5. I don't know if I've had to do this. If you didn't, hit pause and try it, because it's a little different because you're graphing rate. It's not concentration versus time, but rate versus concentration. So rate versus concentration. All right, so then you can memorize how these graphs look, but you don't need to. So here's how you can deduce this. So what we already know. So let's say rate equals K times A, actually have X. So X to the 0 power. All right, so if it's rate X to the 0 power. So if we were to double the rate of X, double, and we raise it to the 0 power, what effect does that have on the rate? Well, it doesn't. It doesn't affect the rate. That's the whole idea of a 0 order. If you have first order, and we double the rate, 2 to the first power, that will double, I'm sorry, double the concentration, that will double the rate. And if we have a second order, because we don't usually go as high as third, although we could, second order, that's going to increase the rate 4 times. So a graph of rate versus concentration, it's not going to affect it. So as the concentration increases, the rate stays the same. The rate stays the same. So if we tripled this, if we quadrupled it, the rate still stays the same. So that's that graph. And this one, if we quadrupled it, it would quadruple. If we tripled it, it would triple. And so the rate versus concentration this time, 1 and 1, 2 and 2. And so you get this nice straight line. That's a terrible graph. You get the idea. 3 and 3. That would be more like 3 and 3. Now doubled though. So once again, rate goes here versus concentration. So if we do, the rate goes, let's say 1, well, now we know the rate doubles. So this is 1 and 1. So that'd be more like there. If we double this, it goes 4 times. And so the graph you would end up with is this exponential looking one, or the square graph. All right. I guess that's it. So that's what I wanted to cover. So there's the answers to that sheet. So if you have any more questions on that, let me know. And as you're trying this one the next few days, there's a lot of different types of questions thrown at you all at once after tomorrow. Tomorrow's a reaction mechanism. Thursday, then we're just not going to do anything new. We're going to practice some of these problems Thursday, Friday. No school Friday, no school Monday. And then we'll pick back up on Tuesday with a review of everything. Right now I have the test still planned for a day next week, but I'm not sure if it's going to be Thursday or Friday. I will let you know. All right.